Hi, we are the DEP Gold Team composed of 5 undergraduate aerospace engineering students. Our project is a Distributed Electric Propulsion Aircraft, or DEP aircraft. Distributed electric propulsion consists of the use of a variety of propellers distributed along the wingspan or fuselage, which allows for a higher flexibility in the design of aircraft and an overall improved performance compared to current electric-powered aircraft. The NASA project guidelines provided for this project gave only one requirement, which is a minimum wingspan of 36 inches. The team decided to give an extra set of requirements to meet the definition of DEP, these being an all-electric design with a variety of motors. The team was additionally given a budget of $500 and to have a small DEP aircraft model. The team decided to not surpass a total weight of 10 pounds. The DEP aircraft design must prove its performance to be above current non-electrical designs and must maintain the fact that the use of batteries without a distributed electric propulsion system is not as proficient. The DEP design must efficiently integrate the batteries that will power the aircraft. The design must provide sufficient lift with the use of a larger amount of motors and propellers throughout the wingspan, without altering the battery's weights to maintain the concept of distributed propulsion.
Today's conventional aircrafts are highly dependent on fossil fuels, which are a high source of current global warming. Electric propulsion is expected to reduce the use of fossil fuels and emission, as well as lower noise pollution. A main disadvantage of electric propulsion is the integration of batteries, as today's batteries are too heavy to give the energy necessary to power a conventional aircraft. Distributed electric propulsion hopes to increase the lift of the aircraft without altering the batteries by integrating a large amount of motors and propellers across the wingspan. DEP aircraft are the future of commercial flights, reducing greenhouse gases, improving flight performance, and reducing the demand for chemical products required in today's aircraft design. For a high-performance design, the team expects to see a thrust-to-weight ratio of 0.4 and a maximum lift of 44.2 newtons.
The team first performed research on existing DEP aircraft and its key components. Initial design specifications are used as the basis for sizing of the aircraft. After detailed analysis, risk assessment, and simulations are performed on each design component, changes and decisions are made to optimize. The wing is first analyzed under specific parameters, and its performance leads to decisions and final specifications, as well as the design of the fuselage, tail, and electric control system. Initially, the team wanted to use a Clark Y airfoil, but after extensive analysis in XFLR5 and ANSYS Fluent, the team decided on a NACA 4415 airfoil, as it showed an increased performance compared to the Clark Y. It displayed a higher lift for different angles of attack and higher lift coefficient values for different aspect ratios. The team decided on an aspect ratio of 8, as analysis showed that this one had high CL/CD performance while maintaining low vortices and maintaining a good size that would not increase the material needed or extend the manufacturing process. For success in design, testing, and manufacturing, the team made sure to follow the following Gantt chart, which would set due dates and reminders to maintain an organized and efficient approach to the project. This chart also contains specific tasks for the team members in charge of a specific component of the DEP aircraft and dates for meetings with the team advisor.
Our motivation for this project is that a well-organized and thorough design of a distributed electric propulsion aircraft will be a step closer to commercial electric aircraft. This will be a large benefit to humanity, as it will reduce air pollution and also aid in the reduction of climate-intensive forms of flying. Successful design and performance of the model DEP aircraft would introduce a design that can be incorporated for future full-scale aircraft, promoting a clean form of air travel. In order to quantify a high-performing DEP aircraft, the team made sure to set requirements, objectives, and goals that the project provided. By identifying these throughout the process of the project, it allowed for the team to make decisions that would only take us closer to the end goal.
Electronics are a crucial part of the DEP aircraft, keeping the plane airborne and allowing it to operate smoothly and efficiently. When selecting the electronic components, multiple different facets need to be considered, such as the voltage, amps, and connectors between each part. With this in mind, the electronic components are as follows. 6 Cobra CM2208 motors that operate under 11.1 volts and 20 maximum amps, 6 20 amp ESCs with UBEC inside, 6 Spectrum 11.1 volt 300 milliamp batteries, A4 SG90 servos for control surfaces, AR620 flight receiver, DX6E flight controller. The motors will each have their own independent ESC and battery to properly power the system. The motors feature 6-inch by 4.5 propellers to accelerate the aircraft. Each individual ESC will be soldered together before attaching to the flight receiver to have each motor operate uniformly to avoid uneven distribution of power. Each servo will plug directly into the flight controller to be able to independently operate each control surface. Finally, the flight receiver will wirelessly transmit to the flight controller to operate the aircraft.
The skeleton of the aircraft is mostly made up of balsa wood, with exception to some Baltic birch wood for the tail. This is due to its high strength to weight ratio as well as its performance under loads as observed in ANSYS Fluent software. The DEP aircraft design is also composed of aluminum rods due to their high strength, low weight, and simple manufacturing, with the exception of 2 carbon fiber rods. The nose cone and the motor holders will be 3D printed.
Stability analysis is the process of determining an aircraft's behavior during flight. Specifically, what the natural state of the aircraft is and whether it will remain in a stable or unstable state after controls are exerted on the aircraft. This is all affected by parameters such as weight, wing design, center of gravity, and control surfaces on the aircraft. For example, using software like XLR5, we're able to locate the ideal placement for the aircraft's final center of gravity, placing it in such a way that the aircraft would want to straighten itself after external forces such as wind or user controls were exerted.
Initially, we put a center of gravity at 25% core of wing and performed longitudinal stability analysis. We analyzed the result by taking a look at CM versus alpha graphs and determined the aircraft would be stable based on the graphs being negative. However, we noticed the trim condition is negative, so we performed several stability analysis with different CG location and came up with better trim condition for the aircraft. We also found the neutral point of the aircraft where we expect it to be behind the center of gravity and locate within the wing. These analyses prove that the aircraft is stable when encountering the gust wing, where the aircraft will try to react and go back to normal flight path.
Aerodynamics are fundamental to a functional aircraft. To ensure that our lift and drag along the smooth airflow was up to spec, simulations were run on ANSYS Fluent. The shell of the plane was modeled and simulated against cruise conditions to ensure that the plane could maintain stable and level flight. As we can see on our models, there's a high static pressure area on the bottom of the wing with a low pressure area on the top. Viewing the path lines, we do not see any strange vortexes or anomalies going on around the wing or the fuselage. After analysis, the plane was able to generate around 50 newtons of lift at cruise angle of attack and 108 at maximum angle of attack.
After positioning the center of gravity at the appropriate spot, we then conduct analysis on how the aircraft respond when external force apply when the controller execute a maneuver. The result shows that the aircraft oscillate back into its position very quickly by the order of milliseconds when roll, pitch, and yaw. In addition, the root locus that represents the aircraft is also in the left side of the graph, indicating a stable configuration when the aircraft experiences change in direction with different modes.
For successful manufacturing, the team must take into account the lead times to receive materials, including components for the manufacturing of the body. While many of the components will either be laser cut, like the balsa wood, or 3D printed, the team must also integrate these pieces. This means epoxying and attaching the balsa wood and metal rods, as well as the components that create each system, the tail, the wing, and the fuselage. Since this is believed to take the longest, it will be the first step in manufacturing. The team is composed of 5 members. However, to ensure accountability, each system will be integrated by 2 team members. Additionally, the electronics and flight controls will be tested and integrated by the entire team.
To ensure a safe, high-performance DEP aircraft design, the team performed a risk assessment where each main system of the aircraft is judged using likelihood, consequence, and detectability scales. The electronics and propulsion system faced the highest score for risk assessment. In order to ensure that all of the electric components work, along with the propulsion systems and the flight controls, the team will set up the electrical components along with the servos, motors, and propellers to assure that the system works correctly. Additionally, the team has performed calculations and research behind the electrical components in order to assure that in case of needed extra power, the batteries will still be able to give out enough energy. For every other system, the main failure was identified as structural failure. A new connector for the wing to fuselage has been created and tested, along with assuring that the material of the connector has high performance when taking into account the loads expected. This connector design consists of an aluminum bar that serves as a main rod of the wing while maintaining stability of it to the fuselage. The advantage of the design is the simplicity to mount and connect to the balsa wood, along with the ease of manufacturing of aluminum material. The strength of the design was tested under expected loads and displayed small deformations.
In manufacturing and integration, the team faced some challenges, mainly in the weight provided by the tail. The team decided to use poplar wood to make last-minute adjustments, as well as using some of the aluminum rod used for the wing connector to stabilize the tail with the fuselage. Further, the team used a thrust test to measure the thrust provided by each propeller and motor and found that each provides a thrust of 4.71 newtons, which gives a final thrust-to-weight ratio of 1.3, taking into account all 6 propellers. The ratio is 3.25 greater than the desired ratio. The team will further perform a flight test to ensure the structure and electronics are working properly, and will finalize with a final flight that will be presented to the advisor.